Welcome to Algorithms and Data Structures course. My name is still Askar Haimultin. Hopefully I'll be your lecturer till the end of this course. So we've already figured out what is programming and its object-oriented concept, and maybe for you it seems there's nothing more left here to say, but we're still comparatively in the beginning. The main focus of this course is designed on solving computational problems that involve collections of data. You will study a bunch of data abstractions, data structures, and algorithms that provide a foundation for creating and maintaining efficient programs and algorithms in particular. Today, we're going to start everything from the topic which is called the recursion. The simplest explanation of that is a function that calls itself. This topic sometimes occurs as a continuation of functions, but I personally decided to use it as a starting point to algorithms. Hence, it's more or less about function calls, method invocations, and things like that. We will start from the recursion overview. We'll see a simple example how that works, what happens inside the stack memory when a method is invoked. We will compare iterative and recursive solution for the same problem, providing you some ideas on how to create a recursive algorithm and finishing with a classic solution for Fibonacci numbers. So far, we have seen methods that call other functions. For example, the main method calls the square function. A recursive method is a method that calls itself. It's the process of repeating items in a self-similar way. The core idea behind that is divide and conquer, which means that we may divide a big problem to a set of smaller subproblems and keep doing the same recursively until that smaller problem becomes simple enough to solve it directly without any other recursive call. In order to understand whether we should keep doing the recursive call or do some immediate action, the recursion itself is divided into two parts: recursive case and the base case. Every recursive method must have one or more base cases. The base case is kind of stopping point for our recursion. We introduce the condition when that, let's say, super subproblem can be solved at once without any need of recursive calls. Basically, the recursive method must solve the same problem on some other input with the goal of simplifying the larger problem input. Here's an example. Let's say that we need to create a method that should calculate the factorial. If you don't remember, factorial of a number is just the product of all previous numbers, starting from 1 including the given one. For example, n factorial is equal to 1 multiplied by 2, that multiplied by 3 up to the n, and it could be concluded as the function of factorial of n. But this can also be simplified to the form of n minus 1 factorial multiplied by n, because the thing that stands before the n is exactly factorial n minus 1. And the next step is also trivial. It can then be represented as n minus 2 factorial multiplied by n minus 1 multiplied by n. And keeping the same strategy, we can end up with 1 factorial multiplied by all other numbers. 1 factorial and 0 factorial are our base cases, since we exactly know what they are equal to. Let me remind you that both 1 and 0 factorials are equal to 1. Now we are ready to write a code for that. As we've mentioned before, we start from defining the base case and recursive case. The base case would be 1 and 0 factorials. In both cases, we return 1 here. For all other cases, which are accepted as recursive case, we return n-1 factorial multiplied by n. Here's the point where a function calls itself. Maybe someone would hate that, but I personally do not like the phrase as function calls itself. In programming, every function that we write, or let's be more general by saying every instruction that we write, is stored in a specific place of our RAM. They are stored in a compiled form in the machine language at lower addresses. So the only function that is going to be invoked automatically is our main function. It does not need any explicit call since it's getting called once you run the executable file. On every method invocation, a new frame is created and pushed on the stack. This frame contains local variables, operand stack, and reference to constant pool. Frame is removed when either method has completed successfully or the method throws an unquote exception. That frame inside the stack is kind of instance of a function, the same as we had an object of a class, where class was just a template or a blueprint. You should understand that all functions that you write are just templates, and instances are created only during the function call. Now see why it's not that accurate to say function calls itself, because it creates a new instance inside our stack, which is then called as a frame. Every of that frame has its own address. They are just physically in different frames. So the call stack, or simply stack, keeps track of the sequence of method calls that have been started but not finished yet. If you remember from Introduction to Programming course, a function call causes a function interruption, which is basically means that a point where you call a function will keep waiting for the completion of that function. And if you do that, if you do that function call recursively, there will be created a number of frames inside the stack, which are created from the same function. There are some disadvantages in using recursion. One of that is miss of base case. Sometimes it happens that one of the base cases is missed. You can just forget or be unable to distinguish one of that stopping points. This leads to stack overflow. Every stack has its physical limits, and if you keep adding new frames on it, that may happen to have no place for one of your frame. That's exactly what is a stack overflow. It simply happens when you exceed the physical memory limit. I can't answer the question as what is the size of stack, since it's sometimes language dependent, or it may depend on your own configurations. Generally, it's much less than your RAM, of course. It could be 1 megabyte or 256 kilobyte, but there's no exact answer. The Java stack inside JVM is even different. And another problem that might occur when using recursion is that a subproblem becomes not easier than the original one. So now we understand that when you run your program, there will be created a stack. Each time you invoke a method, the method is placed to the stack in form of frame. A stack is a last-in, first-out memory structure, which means that the first item referenced or removed from a stack is always the last item entered into the stack. If some function call has produced an excessively long chain of recursive calls, it can lead to stack overflow. This usually happens when we accidentally run an infinite recursion. I hope you remember that it could happen when you miss one of the base cases. Alright, everything's clear I guess at that point. Now let's look at this beautiful animation for our previous code. It was the first time I created a GIF file on my own. Yeah, let's get back to this topic. This animation is an illustration of what exactly happens when you run the code, which calculates factorial of 3 and prints it to the console. When you run this code, the main method is invoked directly, where we say that the variable result is equal to or should store a value which is returned by a function named factorial. We send there 3, and this is exactly the place where function interruption occurs. The main method cannot continue its execution until the function that we've just called finishes. A new frame for factorial of 3 will be created here. Yeah, let's wait a bit. Here we go, waiting for 3. A new frame is here. So we proceed the execution inside that new frame, yeah, for factorial of 3. First of all, it examines the base case. So 3 is not the base case. And then it returns the product of factorial of 2 and 3. But factorial of 2 is our subproblem. It's not a function interruption. It should wait for the value that function returns for factorial of 2. The same will happen for the next frame, but when we get to the point of factorial of 1, we meet the base case and return 1 immediately. So let's look at it again. We examine the base case, wait for factorial of 1, then we return 1. That 1 goes here and goes here. 2 multiplied by 3, 6 goes to the main, then you output that, and in this way. So that 1 goes to the frame of factorial of 2, which then is returned as the product of 1 and now and 2. 1 multiplied by 2 is 2. It's returned further to the frame of factorial of 3. That multiplies us to return 2 by 3 and gives it back to mainframe. Mainframe will use it as a value for variable named result and prints it. In this animation, I didn't show you some other behind the scene operation which might also appear as a separate frame inside the stack. For instance, this system out print line. And because print line is also a function, it also needs its execution. Okay? You know that this everything totally resembles the iteration. So let's compare them. I believe that each one of you can easily write a function that calculates the factorial using iteration. It's just one loop with n steps that multiplies every number step by step. Here's the difference. Iteration uses repetition structures such as while, for, do while, whereas recursion uses repeated calls of the same function with more primitive problem. The ending point for the iteration is loop continuation condition failure, and ending point for the recursion is meeting one of its base cases. If one uses a counter for control, another one uses parameter value during recursive division of a problem. It can also be summarized as that for the repetition, iteration uses explicit loop, recursion uses repeated function calls. The termination occurs in the iteration when loop condition fails, and the recursion when the base case recognized. Both can have infinite loops, but as you may know that having an infinite recursion may lead to stack overflow. So this is kind of a balance between performance and the good software engineering, because if we're talking about the performance, it's more about the iteration. So here's some criteria. If mode of implementation, it uses loops that use functions itself. State defined by the control variables value, yeah, that is controlled by parameter values. the progression, the value of control value moves towards the value in condition, the function state converges towards the base case. The termination occurs when a loop condition fails. Here, when base case is recognized, the code size, iterative code tends to be bigger in size, of course, and recursion decreases the size of code. No termination state, infinite loops uses CPU cycles. Here, infinite recursion may cause stack overflow. And the execution is much faster in the iteration and slower in the recursion. So, how to create a recursive algorithm? A good question, but you should understand that a recursion can give you an elegant, straightforward, easily readable, and little code for a huge problem, but it has nothing with good performance. As we've previously said, iterative solutions provide better performance than recursive ones. Recursion is made for solving problems that can be broken down into smaller, repetitive problems. It's especially good for working on things that have many possible branches and are too complex for an iterative approach. A good example of this would be searching through a file system or finding the path inside a maze. For sure, in this course, you'll be asked to provide exactly recursive solutions, but generally, it should not be the target. So, some steps to create a recursive algorithm. The first is think about the problem at a high level of abstraction without going to the specifics. The second one is figure out the base case for the problem, where your recursion should stop. And the next is redefine the answer in terms of simpler subproblem. And finally, we combine the results in the formulation of the answer. So using this knowledge, let's solve another problem. This is Fibonacci problem. So if you remember Fibonacci sequence, it starts from 0, 1, 1, 2, 3, 5, 8, and so on and so forth. Each element is just the sum of previous two. Let's say 1 plus 2 is 3, 2 plus 3 is 5, and so on. It starts from 0 and 1. So our task is to find the Fibonacci number at the given position. For example, the third element is 2, counting from 0, 0, 1, 2, 3, yeah, the third element is 2, and the sixth element is 8. And if you count, the 8 is the sixth element. So, first of all, we know that our base case is 0 and 1, because we exactly know what is the value for that. When it's 0, it's 0, when it's 1, it's 1. And for all other cases, my Fibonacci n is equal to Fibonacci n minus 2 plus Fibonacci n minus 1. And the solution for that, we'll see here, we say that if my n is less or equal to 1, assuming that n is equal to 0 and 1, we just return n. So for 0 it's 0, for 1 it's 1. And for all other cases, we just return Fibonacci n minus 2 plus Fibonacci n minus 1. Yeah, there's no need to write else statement, because when you write return, it means that you won't go to the next step when you return. Yeah, because return, it exits the function at all. So that is all for today. The literature to read is Algorithms, 4th edition by Robert Sedgwick, chapter 1.1, and Grokking Algorithms by Varhava, and chapter 3. So good luck.